Jelly.
Hey,
all right.
That's just as good.
Okay, so somebody remind me the two models of how enzymes work. We talked about this when we were outside. Carrie, you can give us one, and then Katie can give us the other. Lock and key. So one model of how enzymes work is that enzymes are shaped perfectly for a very specific material to bind to. So that specific material is the key, the enzyme is the lock, the key fits perfectly in the lock, makes magic happen, right? Unlocks, opens that door or that treasure chest.
So lock and key.
Lock and key, and Katie, what's the other?
Induced.
Induced fit. And so the induced fit says that the enzyme isn't shaped perfectly for what it's going to bind to, but it has the perfect chemistry for what it's going to bind to.
So it'll bond.
Yeah, so the chemistry and the enzyme will basically change its shape to fully what I want to say embrace, and that's the best word that I can think of. The enzyme will change its shape to fully embrace whatever it is that it's bound to. Okay? It's almost like this idea here. To fully embrace whatever it's binding
What do
to.
you mean embrace?
To give it a hug.
To give it a hug. Yeah, absolutely.
I love hugs.
And so the idea of induced fit is kind of this. The enzyme's sitting here like this, looking for something to hug. Okay? And the chemistry on this surface matches something very specific. And so it attracts something very specific. Once that specific material gets there, then the enzyme changes its shape and wraps that material up in a nice embrace. Okay? Because what do enzymes actually do? How do they help reactions go faster? This is something we talked about last week as well. Kyle.
They lower the activation.
They do lower the activation energy. And so even in a reaction that releases energy, it takes some amount of investment to make that reaction happen. And why is that? Why do you have to invest a small amount of energy, even in a reaction that releases energy, where the products, even if the products have way more free energy than the
Don't you
reactants?
just have to have something to like ignite it?
Yeah, well, yes. So that energy could be a spark, or that energy can be something else. But why do you need that initial energy?
To get it started.
Well, yeah, but what's happening? What's needed? To break bonds, right? So in chemical reactions, you've got to break bonds before you can make new bonds. Okay? And breaking bonds requires energy. We've got some activation energy. As Kyle so eloquently reminded us, enzymes lower that activation energy. True or false? Enzymes change the thermodynamics of a reaction.
Oh no, they don't. Right?
False, right? So the amount of free energy in the reactants is this, and the amount of free energy in the products is the same whether or not you use an enzyme. All the enzymes are doing are speeding the rate of reaction. Yeah, Isa.
Is the last thing we talked about the ADP plus PC enzyme lowers activation energy?
I think so. Yeah, because we talked about delta G before we went outside, right? Where if you want to know whether or not a reaction's going to be spontaneous, you determine your delta G. If delta G is 0 or positive, it is what? Spontaneous or non-spontaneous? Non-spontaneous. If delta G is negative, it is spontaneous. Delta G is equal to delta H minus T delta S. Okay? And so again, delta H, you can think of this as the change in the internal energy in a system. It's a measurement of the free heat in a system. And so there are two ways in which delta G can be negative. This number can be really negative, right? So which means you could lose a lot of free heat from your system. Or what else can happen to make delta G negative? So either this needs to be really negative, so you're going to lose a lot of that free heat.
Or the other one has to be negative.
Or this has to be really positive since we're subtracting it away. And delta S is a measurement of the change in what?
Oh, I think I energy.
This is free energy. Entropy, which is a measurement of randomness. So if this is really positive, it means you're vastly increasing the randomness.
Wait,
Okay.
the what measurement of randomness?
Measurement of randomness.
I just put amount of disorder.
Yeah.
That works too. Disorder, randomness, tomato. Have I told you all that my 3-year-old she says tomato
Does she?
and potato because she watches Peppa Pig, and then she corrects us for saying tomato. She's like, Mom, that's not how you say it. It's tomato. It's adorable. All right. And then my son, his teacher is from England, and he says all of his classmates' names with a British accent. So he hasn't taken anything else from her, but he's got a classmate, one of his good friends, his name's Tori, but his teacher says Tari, and so he thinks his name is Tari. And I'm like, no, his name is Tori. He said, no, Mrs. Khalifa says it's Tari. Alright, okay. Does this make sense?
Yes.
Okay, we're good.
Wait,
All right.
so wait, what is, changing gives free energy.
Yep.
Enthalpy, temp.
Yes, and so enthalpy, you can think of it as the measure of free heat, or the heat content of a system, or the amount of, internal energy. Yeah. Alright. Cool. Alright, so enzymes do not change the thermodynamics of a reaction. The thermodynamics of a reaction are determined by this. Enzymes do not change that. They lower the activation energy, make the reactions happen faster. Something else that's true about enzyme catalyzed reactions is enzymes are not used up by the reaction. The reactants are used up and are converted into product, right? That's what happens in a chemical reaction. Isa, give us a chemical reaction, the one that you always go to.
Fire.
Fire, right? And so what are the reactants in a fire?
Carbon dioxide.
Carbon dioxide is a product.
Oh.
So some carbon-containing material could be wood, right? A lot of carbon-containing material and oxygen. Okay? Those are our reactants in a combustion reaction. Both of which get used up, right?
Yeah.
You throw a piece of wood on a fire, eventually you have no wood left.
Wow.
Right?
That's how
Okay.
fire works.
And have you ever put out a candle? Look at this. Great for the illustration. Yeah, you put the lid back on, and eventually it burns up all the oxygen present in there and it goes out. Okay? And so in a chemical reaction, your reactants are converted into product. In an enzyme catalyzed reaction, the enzyme is not lost. So you have something that looks like this. Okay? Initially, you should write this down. This is a really good little flow chart. This is really good. This is a really good flow chart.
What's the E?
E is for enzyme.
What's S?
I'm glad you asked. So I mentioned a term, and so in chemistry we would call it R for reactant, but in biology when we're talking about enzymes, we don't call it R for reactant, we call it S for substrate. Substrate.
What's P?
P is product, same as in a chemical reaction. Alright, so in our lock and key model of enzyme activity, the substrate would be the key. E is enzyme. Sorry, let's get that labeled. This is a good flowchart, right?
That's great.
Merry Christmas, everyone. So in a lock and key model of enzyme activity, the substrate would be the key, the enzyme is the lock. And this substrate is perfectly shaped to fit inside of the lock. Okay? In induced fit model, the enzyme's the great big bear waiting for the hug, right? And then the substrate's the thing that chemically is perfectly designed to be attracted right here so that the enzyme can then change its shape to embrace that substrate. Alright? So here's our flow. We start here with enzyme and substrate both in the mix. Then what happens? They come together and we have what's called the enzyme substrate complex.
Whoa.
Enzyme substrate complex. They're now together. Either the lock or the key is inside the lock, or the substrate is wrapped up in the embrace of that enzyme. Right? Either way, we form our enzyme substrate complex.
Wait, what is this thing? What are we doing?
This is the flow as you move through an enzyme catalyzed reaction.
Okay.
So in a chemical reaction, you would just go from reactants to products.
Yeah.
And that's all you'd write down, that's all you'd keep track of. But that's boring, right? And that's missing some information. Welcome, welcome. Oh, wow. Thank you. Okay. Does that make sense, Issa?
Enzyme catalyst reaction?
Enzyme catalyzed reaction. Yeah. 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 Okay, so we start with enzyme and substrate separate. Now we have our enzyme substrate complex. And then we go to an enzyme product complex. And then we go to enzyme and product separate. The product is released from that enzyme and allowed to, I don't know, go wherever it's going to go. With most of our metabolic processes, this product would become the substrate for another enzyme. And you'd have a whole chain of reactions. When we come back in January, we'll talk about glycolysis, and you'll love it. You probably talked about glycolysis in Honors Bio, but we're going to talk about it in some pretty awesome detail. And you'll see that the product of one reaction becomes the substrate for the next. Okay? But notice this enzyme that's part of the end of this flow chart now gets to start another process. That enzyme is not used up in the reaction. The substrate is used up in the reaction, right? The substrate disappears. Do you see that?
Wait, where'd it go?
That's a wonderful question. It became the product. It was chemically modified. So there's substrate, all of a sudden the substrate's gone because it was converted into product. Yeah, Emma.
So, in the top, there's an ES. Can you explain the top and here? How do they combine?
Yeah, well, there are two models for how they combine. Either the substrate was perfectly shaped to fit inside the enzyme, or the enzyme changed its shape to embrace the substrate.
Yeah, but how is that not a product?
How is it not a product yet?
Yeah.
Because it's still the substrate, it's just the substrate chemically and physically bonded to the enzyme. It doesn't become the product until the chemical reaction takes place. Yeah, that's a good question. Alright? Does this make sense? Do you love it?
I love it.
Oh, I'm so glad. Okay? So that reviews and gives you a little bit more details of what we were talking about last week on Friday. I think that was when we were talking about this. Feels right. So what is this? Substrate. And what do these brackets mean? We've seen this before in this class. You've seen this in chemistry. Yeah,
Is
Emma.
it like for a bond? And then you put like the charge?
You could if it's dealing with like Lewis dot structures. You do see it some
Oh, those
there.
are fun. Remember that.
This is substrate concentration.
Concentration.
Oh yeah. You should, just like you put this flow chart into your notes, and I need you to care. I know we're at that time of the year where you're like, Dr. Engel, I'm literally like 5 hours away from being done because tomorrow's not even a real school day.
Wait, do we have to come tomorrow?
I don't have to come tomorrow. If you don't come tomorrow, you will be marked absent. I don't know what that
Great
means.
observation.
Okay. Okay, so just like you put this flow chart into your notes, you should put this graph into your notes because it's a good one. It's a great one.
Oh.
Yeah.
What's the little arrow under the substrate concentration?
It's just showing you that it's increasing in that direction. And then reaction rate is increasing in this direction.
It's going that way.
Okay?
Yeah, that way.
Alright. Check this out. Check this out. So what this is saying is as we increase substrate, what's going to happen with our reaction rate? And what do you think? Let's go back to this flow chart. If we increase the amount of substrate we have, what should it do with the reaction rate? Should it speed it up? Should it slow it down? Should it have any impact on the reaction rate?
I think it would slow it down because it take more time to convert and stuff.
Okay. It would take more time to convert every single substrate molecule, right? but overall the amount of product we're making should increase, right? Okay. So here's what it looks like. Complete this graph. Have this graph. Okay, are you ready?
It's gotta be just positive. Oh, it curves.
Okay.
Wow.
I gotta wait a second.
Wait, so the more substrate, the same reaction rate?
No, the more substrate you have, the faster the reaction rate. So reaction rate increases this way, substrate increases this way. The more substrate you have, the faster your reaction rate until you get to what's called the Vmax. Okay? Vmax, which this is the fastest rate. And I want to ask you this question. What is going to determine the fastest rate of this reaction? Yeah, Tori.
The substrate concentration.
Substrate concentration. Well, notice we get to a point where we keep adding more, but it's not actually increasing the reaction rate.
Oh.
Yeah, so what about the enzyme, Kyle? Yeah, what about
The
it?
quickness in which it hugs.
Yeah.
So what's going on here? So we get to a point that we're adding more and more substrate, but it's not speeding up the reaction. Why? Gosh, Rick.
It's as fast as the enzyme can go. Already.
But why? Katie.
Because like the enzyme's so outnumbered by the
Yeah, the enzymes become saturated. Okay? You get to a certain point where all your enzymes are working and they have to wait until they finish this flow chart to go again. Okay? So you can keep raising Vmax by doing what? Adding enzyme. So the Vmax is determined primarily by your enzyme concentration. You add more enzyme, your Vmax increases. It makes sense? That's awesome, right?
It's pretty awesome.
Because you get to a point where if you add more substrate, well, first of all, the amount of substrate you have does nothing to Vmax. Okay? The more substrate you have, the closer you could get to Vmax, but Vmax is determined primarily by what?
Enzyme set.
Enzyme concentration. Yep. By your enzymes becoming saturated. Okay? Yeah, Rick.
Can you ever reach the Vmax, or is it just like
You well, I mean, in theory you could, but it's basically asymptotic. Like you get to a point where you're getting infinitely closer to Vmax, but you'll probably never actually reach Vmax. But if you're like at 99.99% of Vmax, you're pretty much at Vmax, right? Right? Isn't this great?
It is.
I mean, this is so good because it shows you that the amount of enzyme you have is incredibly important in impacting reaction rate, and also that the amount of substrate you have is incredibly important in impacting reaction rate. Yeah, Isa.
What are the amounts like about?
What are the amount? Well, it depends on the enzyme.
Okay, I'm gonna
You want to know like what do you want to know amount of what?
Alright, well let's start with the stupid question first.
Okay, I love it.
Enzyme.
Well, an enzyme is a protein that's going to catalyze a reaction.
Right.
Yeah.
So how many enzymes are you talking when you say like the Vmax? Like
It depends on what the enzyme is. So inside of this pineapple juice, which we'll use for our lab, this is 100% juice.
Oh shit.
Okay, only the best for you. So inside of this pineapple juice, there is an enzyme called bromelain or bromelain. I've heard it pronounced both ways. I call it bromelain. Anyways, there's an enzyme in here that digests proteins.
Which is wait,
Is that what
is it an
pineapple juice
enzyme
makes your
protein?
heart hurt?
I think no, it gives you heartburn because it's acidic. Yeah. All right. So there's an enzyme in here. There's an enzyme in here that digests protein, and this enzyme concentration is really, really high inside of the pineapple juice. So when you're talking about how many enzymes there are, I mean hundreds of millions, probably, maybe more. Yeah.
So you said enzymes are proteins, right?
They are.
And then you said the enzyme that was in there digests proteins. How can protein digest?
That's a wonderful question. The digestive enzymes are almost always proteins. And so it requires proteins to break down proteins. It requires proteins to build proteins. It requires proteins to break down proteins. Which is an interesting question of which came first, the protein or the ability to break it down, knowing that that's also a protein. And it required a protein to build that protein.
Circular
So
causality.
the protein that built the protein.
He taught me that.
The protein that came first and the protein that built
Yeah, proteins are wonderful in that every protein that a cell makes requires dozens of proteins to make it. And so in order to make any protein, you need other proteins. And then it's like that's one of the reasons why the cell theory says cells come from pre-existing cells. Right? Because you have to start with a certain mix of materials. Right? So you know, a human being, we start as a zygote, which is an egg fertilized by sperm, right? But the egg is already full of those proteins necessary to develop a new human being. So at some point it had to start, right? At some point you got to violate the cell law. Okay, anyways, all right, back to this. Okay, yeah.
Is it really a law if you have to violate it at some point for it to exist?
Oh, sure.
Okay, never mind.
Right, at some point the law has to be put in place.
Yeah.
Yeah,
Okay.
yeah. Okay. So, can you think of anything else that we can do to raise Vmax besides adding more enzyme? So that's one way to raise Vmax. Add more enzyme.
Lower the rate.
Lower the rate. What do you mean?
So, if like you have to go up, like your reaction rate is always going up, right?
Well, up until you get to Vmax. So this, remember when we talked about carrying capacity? Okay, and like there's just a certain number of individuals that an environment could sustain.
Yes.
This is sort of the same idea, but with a reaction,
So
right? There's a certain maximum rate. Yeah.
So Vmax is the maximum reaction.
Yes, but yes. Now, just like you can increase carrying capacity,
Yeah.
right? Because carrying capacity is determined by a number of factors.
But you can't increase Vmax.
You can by adding more enzyme.
By adding more what?
Enzyme. If you add more enzyme, it's going to increase Vmax.
So Vmax isn't like a set thing.
It's set for a particular enzyme concentration.
And what's that?
Well, it depends. It varies from enzyme to enzyme and reaction to reaction.
So you could have a Vmax of like a low enzyme, and you could have a Vmax of like a high enzyme concentration?
Yes. Yep. It also depends on how complex the reaction is you're trying to catalyze.
It's not distracting at all.
That's helpful. Okay. So more enzyme. Look at this up arrow. It's going to increase Vmax. Can you think of any other ways we might increase Vmax? Katie.
By decreasing the amount of concentration in the substrate.
Decreasing the. What do you mean? Well, so if we. The amount of substrate will get us closer to Vmax, but it's not going to impact actual Vmax. So another way we can do it
Increase substrate, decrease enzyme.
is more heat.
Oh.
What happens when things heat up?
They go faster.
They speed up, right? And so when things are going a lot faster, they're a lot more likely to collide. Do you agree?
That's true. When
Think
you're
about.
driving 80 miles
Have any of you ever been ice skating?
I went yesterday.
Oh man, it's so fun.
I don't ice skate.
I,
Ice skating, right?
I love ice skating, and surprisingly, I'm really good at it.
Me too.
Play
My
on
dad
ice.
sucks.
Okay. All right. So think about this. You've got 20 people on the rink, and they're all going really, really slowly.
I
Not-
was way faster than all of
Not
us.
very likely that you're going to get some collisions, right?
Right.
Right?
Really bad.
Now let's add some more skaters. Now instead of 20, you've got 200 people on the rink.
I think I'm more.
Now you've got a lot more likely that you're going to have some collisions, right? This is the whole idea of the substrate. We're increasing substrate. We're increasing the rate of those collisions. Another way you can do it is increase the speed of the skaters. And that's what happens when you add more heat. Okay? Until you get to a certain point.
So when you add more heat, you're increasing
The reaction rate. You're increasing Vmax. Yep, you're adding more enzyme is going to increase Vmax, adding more heat is going to increase Vmax. Up to a point.
Can adding more enzymes add more heat automatically, or do you have to add more heat manually?
You'd have to do it manually. Okay. Alright. So I have one more graph I want you to draw. I have one more graph I want you to draw. Okay? And it's this one. Reaction rate. You see this? Reaction rate. Temperature. Okay? So here reaction rate is increasing on the Y. Temperature is increasing on the X. I just told you that adding more heat can increase Vmax, right?
Very positive.
In the same way adding more enzyme can. Up to a point. And here's what it looks like.
Whoa!
I really don't like the way that looks.
I'm sorry.
Very steep drop off.
That's for a good reason. Okay, so we've got our rate of reaction is increasing with more temperature until we get to a certain point, and then it starts decreasing rapidly. Okay, it does look like a shark fin. All right. So we would call this.
Dr. Engel,
Yeah.
do you go to the beach?
Do I go to the beach? Occasionally.
Like, do you go in the water?
Yeah, of course.
Okay, good. Just make sure you're normal.
Wait. Makes a lot of nice.
Yeah.
Nice.
You know what's a lot of fun?
What?
Is to get on a boat that'll take you out far enough into the ocean that you can't see the shore anymore, and then you get in a kayak and kayak around when you can't see land in any direction.
Eaten by sharks.
It's really trippy.
No, it's crazy.
It is really
All
trippy.
on cruise, like, this person doesn't do anything. All around you is just ocean.
You're right.
Okay, this right here. Okay, this right here is the optimal temperature. So as temperature increases, reaction rate should increase. That makes sense, right? Ice skaters on the rink. The faster the ice skaters are going, the more likely they're going to collide.
What's optimal temp?
It depends on the enzyme. These graphs are deliberately generic. Isa.
Optimal temp, like the highest, like,
It's where your Vmax is going to reach a maximum based on temperature. Okay? Now what's going on after here? Why do we get to a point to where increasing the temperature starts to slow the reaction? What's going on?
It's too hot.
It is too hot, but what's going on? Why is it too hot? Why does that matter?
The burn in the enzyme.
What's happening to the enzyme?
stuff because it's heat.
So think about what's going on when you cook an egg.
It boils.
It boils.
If you boil it, it boils. But if you stick it in a frying pan, it goes from clear to white.
Yeah.
Why is that happening?
Because it's been uncooked.
It is becoming solid because the protein in that egg white is unfolding,
Oh.
right?
The heat is releasing it.
So the heat is actually breaking the bonds that hold that protein in its three-dimensional shape, and the proteins unfold, and that's why you can't uncook an egg. You can't reverse that.
You can't uncook that.
Exactly, because you've unfolded those proteins.
You're right.
That's what happens during the cooking process.
I'll be like, nah, I want my flour back.
So what's going on here? As we start to see this steep decline, what's going? The enzymes are unfolding.
Whoa.
Enzymes are unfolding. And you get to a certain temperature at which there are 0 enzyme molecules left, because you've reached a temperature at which all of them are going to be unfolding. All right? What happens then? You can no longer catalyze that reaction with an enzyme. If it's a spontaneous reaction, it'll still happen, although it may take a really, really long time to happen. All right? So we have one more thing we actually need to talk about from chapter 8, but I don't want to talk about it now. We'll talk about it in January when we come back. And it's regulation. Okay? How do we regulate how well an enzyme works? Because this right here, we're just talking about changing the rate of the reaction by adding more enzyme, or adding more substrate, or adding more heat. So does this make sense?
Yeah.
You get to a certain point where the enzymes start unfolding, and if the enzymes unfold, they can't work as they can't grab those substrates anymore.
Wow.
Right? It's whether it's the induced fit, and you've got an enzyme waiting with its arms open wide to embrace the substrate, or the enzyme's like a lock waiting for the key. Nothing.
Good like Me and Carrie are really good at